A 340-meter rock will pass beneath our own satellites, below the machines that carry your GPS, your weather forecast, your live television. Not beside them, beneath them. The date is April 13th, 2029, and something close to 2 billion people will be able to watch it cross the sky with the naked eye. It has a name, Apophis, and it will be the closest approach of an object this size in recorded history. Close enough that Earth's gravity reaches out and grabs it. It won't hit us. That part is settled, but the harder you look at this thing, the less it behaves like a solid object should. Too light to be solid, shaped like two lobes joined by a thin neck, tumbling in a way an ordinary rock has no business tumbling. So here's the question that's quietly unsettling the people who study it. How does something this big pass this close? And why does the word they keep reaching for, every single time, is strange? That word, strange, has followed this rock since the moment we found it, and the name we gave it tells you exactly how strange things got, very quickly. December 2004, a team at the Kitt Peak Observatory in Arizona picked up a faint moving dot. Routine survey work. They logged it, calculated an orbit, and then someone ran the numbers forward, and the numbers came back wrong. Not wrong like a data error. Wrong like, this thing is on a path that intersects Earth. December 2029, impact probability non-zero. Then the observations accumulated and the probability climbed. Within days, it hit 1 in 37, the highest odds ever assigned to a large asteroid in the history of tracking them. 1 chance in 37 that a rock 3 times the length of a football field would strike the planet. The team that named it reached for Egyptian mythology, specifically for Apophis, the serpent of chaos, the ancient enemy of Ra, the creature that existed for one purpose, to swallow the sun and end all things. That's the name they chose? Not cautiously, not ironically. They looked at the odds and named it for the end of the world. The impact window eventually closed. Better data pushed the probability down and then out. Apophis would miss for 2029 and for decades beyond. But here's what that history leaves behind. If this was once the most dangerous cataloged object ever tracked by modern science, why do the scientists who study it now sound almost eager, almost excited for it to arrive? So how did we go from naming it after the serpent of chaos to knowing, with confidence, it won't touch us? That answer took 17 years of work, and the final proof came from a direction nobody expected. When Apophis was first cataloged, the orbital data was thin. A short observation arc means a wide cone of possible future positions, and that cone kept clipping Earth. Every time new measurements came in, scientists narrowed it, ruling out 2029, then 2036, then 2068. Each time, the probability didn't gradually fade to zero. It would hold, then collapse, then hold again at some smaller number, like a card trick where the same card keeps appearing. The decisive moment came in 2021. Using radar, bouncing radio waves off the asteroid, and timing the echo, astronomers pinned its orbit down to within 100 meters. 100 meters of certainty across a solar system. And at that resolution, the threat simply vanished. Not reduced, not deferred. Gone, for at least 100 years. No credible scenario in the next century ends with impact. Which is where something quietly shifts in how scientists talk about Apophis. When the question was, will it hit us? The answer consumed everything. Now that it's answered, definitively, for our lifetimes, a different question moves into the center of the room. Not whether it will strike Earth. That's settled. The question is, what happens to Apophis itself when it arrives? And it turns out that a near miss at this distance, at this size, may be stranger and more revealing than any impact ever could be. So the question shifts from impact to encounter. And the encounter itself turns out to be unlike anything we have a precedent for. Here is what the numbers actually mean. Apophis will pass approximately 31,000 kilometers above Earth's surface. That sounds like a comfortable margin until you set it against something familiar. The satellites that carry your weather forecast, your live television, your GPS coordinates. Those orbit at roughly 35,000 kilometers. Apophis will fly beneath them. A 340-meter rock, threading the gap between the planet and the machines we depend on daily. That is not a near miss in the casual sense. That is the closest any object this size has ever been recorded passing to Earth. Ever. In all of human observation. And it raises a question that nobody had serious reason to study before this moment. because nothing this large has ever come this close to let us study it. What does a planet actually do to an object when it gets this close? Not a glancing blow, not an impact. Something in between, a sustained gravitational conversation between a world and a mountain-sized rock for several hours at intimate range. Earth's gravity at that distance is not trivial. It pulls. It squeezes from one side and releases the other. It generates something called tidal stress, and whether Apophis can withstand it depends entirely on what Apophis is actually made of. And that, it turns out, is where the strangeness starts. So, what is Apophis actually made of? That question sounds simple. It isn't. To answer it, you need to know how much it weighs, and that's where the first strange thing surfaces. Astronomers can estimate Apophis's size from how much sunlight it reflects. They can model its shape from the way that light changes as it rotates. From those two things, you get a volume. And from volume, if you assume you're dealing with solid rock, you get an expected mass. Apophis doesn't have that mass. It's lighter than it should be, significantly lighter. For an object its size, composed of the kind of silicate rock its surface spectrum suggests, the density should land somewhere around 2.5 to 3 grams per cubic centimeter. The measured density comes in well below that. And the gap isn't a rounding error. It means something. The most straightforward explanation is that Apophis isn't solid, not in the way a boulder is solid. Up to a third of its interior, possibly more, maybe empty space, voids. Gaps between loosely packed fragments held together not by strength but by the weakest possible force. Their own mutual gravity, barely. Geologists have a name for this kind of structure. A rubble pile, not one rock, thousands of them, or millions, loosely aggregated into something that looks like an asteroid from the outside, but is closer to a gravel heap held in a shape by nothing but its own faint self-attraction. Which immediately opens a harder question. If it's not solid rock, what is actually holding it together? And what happens to that grip when Earth starts pulling? That gap between expected mass and actual mass isn't just a data anomaly. It's a window into what Apophis physically is. And what it physically is turns out to be something that challenges almost every intuition you'd bring to the word asteroid. Picture a demolition site after the crane has finished. Chunks of concrete, rebar, gravel, broken-facing stone, all piled on each other. Not fused, not cemented, just stacked under their own weight. Now remove the weight. Remove the ground. Float that pile in space. Let mutual gravity pull it gently inward over millions of years, and let it slowly rotate into an approximate shape. That's Apophis. Fragments ranging from dust grains up through boulders potentially meters across, pressed together by a gravitational field so faint it barely registers. Here is what that density measurement actually means in physical terms. The grip holding this asteroid together is almost nothing. Its own gravity is so weak you could crumble a piece of it in your hand and it would drift, not fall. There is no tensile strength. No molecular bonding between the pieces, just mass attracting mass across distances measured in centimeters, and that attraction totaling something close to a whisper. A solid rock weathers force. A rubble pile redistributes it, or doesn't, which is exactly why the low density matters far beyond mere geology. If Apophis is barely holding itself together under its own gravity, what happens when a gravity several million times stronger than its own reaches out and grabs it? What reaches out and grabs it is a tidal force, the same physics that makes Earth's oceans bulge toward the moon. And when that force meets a rubble pile shaped like Apophis, the geometry suddenly matters enormously. Apophis is not a sphere. It is not even close. The best radar imaging we have resolves it into two distinct masses, one larger, one smaller, connected by a narrow bridge of loosely packed material. Scientists call it a contact binary. Two bodies that drifted together at walking speed sometime in the ancient solar system and never quite merged. The neck between them is real, measurable, and thin. That shape is common enough among small asteroids. But common does not mean safe. A sphere distributes stress evenly across its whole body. Two lobes joined at a narrow neck do not. Every force applied to the system, rotation, gravity, the push of sunlight, concentrates at that junction. The neck is not reinforced. It is the thinnest, loosest, most loosely bound point on the entire body. That thin neck is the single weakest joint in the whole body, and it is pointed at us. which raises the question that will define the 2029 encounter before it even begins. Can that neck survive the strain? We know exactly where the weak point is. What we do not know yet is whether Earth's gravity will find it. And the neck isn't the only thing about Apophis that refuses to behave. Most asteroids spin the way a top does, a single, clean axis, predictable, stable. Apophis doesn't. It tumbles. And not in a simple way. Picture a coin someone flipped and set spinning on a table at the same time. So it's rotating around its own center while also precessing around a second axis tilted away from the first. The two motions run simultaneously, neither canceling the other out. That's what Apophis is doing, wobbling on two axes at once, so its orientation in space traces a slow, looping, never quite repeating path. There's no fixed pole, no steady rotation you could set a clock to, just this restless, compound tumble that shouldn't be there. And here's why that matters more than it might sound. Rotation is not stable in a vacuum, it's just slow. Over long timescales, internal friction inside a body like Apophis acts as a damper. Stress waves move through the rock, energy bleeds out as heat, and the spin gradually simplifies. Given enough time, millions of years, billions of years, even a chaotic tumble flattens out into a single clean axis. Physics is patient, which means if Apophis had been tumbling since the solar system formed, it would have stopped tumbling long ago. The fact that it hasn't points to a disturbance that is, by geological standards, almost embarrassingly recent. Not millions of years, thousands. Something knocked this rock out of a clean spin while our ancestors were learning to write, which forces a harder question than the neck ever raised on its own. What keeps knocking this thing out of a clean spin? The answer, at least in part, is sunlight. Not a collision, not a closed pass, not some catastrophic ancient strike. Sunlight. During the day, Apophis absorbs solar radiation. At night, it re-radiates that heat back into space. And because a tumbling, irregularly shaped body doesn't shed that heat evenly, the emission is always slightly off-center. One face cools faster than another. One slope radiates a fraction of a second before the next. Each pulse is effectively nothing. The force is genuinely comparable to the weight of a single paperclip pressing against a mountainside. But it never stops. Year after year, decade after decade, over millions of years, that whisper of pressure accumulates. It has a name, the Yarkovsky effect, and it is almost certainly one of the things slowly twisting Apophis's orbit and feeding that stubborn tumble. A force no stronger than the pressure of daylight has been steering a mountain for millions of years. That should rearrange your sense of what matters in deep time. Even the void isn't neutral, it pushes, which makes the next 7 years suddenly more interesting. Right now, the nudge is imperceptible, but in 2029, Apophis stops being alone with sunlight. It gets something far less gentle, the full gravitational grip of a planet. If something as faint as sunlight can move it, what will a whole planet's gravity do? A planet's gravity doesn't pull a small body as a single point. It pulls the near side harder than the far side, because the near side is closer, and gravity falls off with distance. On a rigid rock, that difference is trivial. The object resists, holds its shape, and the tidal stress amounts to nothing you'd notice. But Apophis isn't a rigid rock. It's a pile of rubble held together by almost nothing, a loose congregation of fragments, dust, and voids, clinging to itself mainly through its own faint self-gravity. And when you run the numbers for a body that size, at the distance Apophis will pass in 2029, Earth will be pulling its near side measurably harder than its far side, hard enough that the asteroid will feel a real stretching force along the line between itself and us. Not a nudge. A structural load. The rubble pile that sunlight has been quietly sculpting for millions of years will, for the first time, be asked to hold itself together under something heavier than a paperclip. Which raises the question no one has fully answered yet. Will that stretch be enough to actually change Apophis? To crack it, shift it, loosen something that was already loose? That question is exactly what 2029 is going to answer, because the mechanism is already set, and it's simpler and more violent than most people realize. The stretching force is real. Now here's what it actually does to the surface. Apophis, under tidal stress, will experience something that sounds almost mundane until you picture it at scale: a landslide. Not a metaphorical one, a literal rearrangement of material on the face of a 340-meter rock, hurtling through space at tens of thousands of kilometers per hour. The models predict that as the tidal load peaks during closest approach, slopes that have been stable for millions of years will cross a threshold. Grains that were sitting comfortably on a gentle incline will suddenly find themselves on a slope that's too steep for the new gravitational environment, and they'll move. Small avalanches, material cascading into low-lying regions, the surface texture reshaping itself over the course of hours. But that's the conservative version. The reserved beat, the one that changes how violent this gets, is what happens to the largest pieces. Boulders could migrate across the surface entirely, and dust, in the regions where tidal flexing momentarily relaxes Apophis's own self-gravity, could actually levitate off the ground. Not launched by an explosion, just lifted, because the grip holding it down briefly loosens its fingers. Which immediately raises a harder question. If the surface is moving, shifting mass, changing how weight is distributed, does the tumble change too? And more importantly, can we actually watch it happen in real time? That would be the first visible effect of the flyby that anyone on Earth could see. So yes, the surface moves. But moving mass means moving weight. And moving weight on a body that's already tumbling in a non-uniform way doesn't leave the tumble untouched. It nudges it. The redistribution of material, boulders migrating, dust settling into new basins, slopes collapsing and filling, changes where Apophis's mass is concentrated. And that changes how it rotates. Not dramatically, but measurably. The tidal forces themselves also apply a direct torque during closest approach. A twisting pull that peaks and then releases as Earth recedes. What comes out the other side isn't quite the same spin state that went in. The rotation period, the wobble, the orientation of the tumble axis, all of it gets perturbed. And here's what that means in practice. The rotation state we will have spent years carefully measuring before 2029 may simply not match what Apophis looks like afterward. Earth will have effectively reset its clock. Rewound the tumble into a new configuration we didn't predict and couldn't have, because the exact surface redistribution was unknowable in advance, which immediately opens something uncomfortable. If even the spin changes, the most basic physical property of the object, how confident can any model really be about the rest? The flyby doesn't just stress the body, it feeds back into the very wobble we used to build the model in the first place. That feedback problem isn't just philosophically uncomfortable. It has a direct, practical ceiling on what any model can actually promise. Because Apophis isn't a billiard ball with known mass at every point. It's a rubble pile, a loose aggregate of fragments, voids, and dust. And the behavior of that kind of structure under stress is chaotic in the technical sense. Small differences in the initial conditions produce wildly different outcomes. Change one boulder's position by a few meters, shift a single subsurface void by a fraction, and the outcome forks. The crack propagates differently. The surface slumps in a different direction. The torque lands on a different part of the neck. Scientists won't commit to a single answer about what happens at closest approach. And that's not a failure of effort. It's an honest acknowledgement of where deterministic physics runs out. The system is too sensitive, the structure too unknown, the interior too dark to map cleanly from the outside. Every prediction comes with a branching tree of plausible alternatives rather than a confident line, which is a strange place to be, given how precisely we know the orbit. We can tell you where Apophis will be to within kilometers. We cannot tell you what it will look like when it gets there. And strange, it turns out, also means unpredictable. So if we can't predict it, why not just wait and watch? So we wait. And what we get in exchange for waiting is something no space agency could ever fund, plan, or ethically propose. A planet-scale stress test, run for free on a rubble pile we've been studying for 20 years. To do this deliberately, we'd have to drag an asteroid past Earth ourselves, engineer a close approach, time it, instrument it. Instead, one is simply coming. On a schedule we've known for decades, at a distance we've pinned to within kilometers, in a geometry that puts it inside the ring of our own geostationary satellites. The universe is running the experiment whether we're ready or not. The only question is who shows up to take notes. And the answer to that is almost everyone. At least a dozen space missions are already in various stages of planning or approval, all timed to be at or near Apophis during the flyby. Ground telescopes on every continent will be locked on. The James Webb, Still operational in 2029 barring disaster, we'll have a view. Amateur astronomers with backyard equipment will be able to track it with the naked eye for the first time. That's why the scientists working this problem aren't afraid of 2029. They're impatient for it. The chaos in the models isn't a threat, it's the question. And in a few years, the rock itself will answer. Almost everyone, it turns out, means almost everyone in the most literal sense. Ground observatories, yes. Webb, yes. But the real prize goes to the spacecraft that will actually be there, in orbit around Apophis, watching from a few dozen kilometers away, as Earth pulls it through the closest gravitational squeeze it's experienced in millions of years. NASA's OSIRIS-APEX is the mission that earns that position. You might know it under its old name, OSIRIS-REx. The probe that flew to asteroid Bennu extended a sample arm and brought a chunk of it back to Earth in 2023. The sample capsule landed in the Utah desert. The spacecraft kept flying, and when mission planners looked at its remaining fuel and its orbital trajectory, they realized it could reach Apophis. Not just fly past, but actually rendezvous and slip into orbit around it, arriving right as the flyby happens. A spacecraft that already grabbed one asteroid is being repurposed to chase a second one, just as Earth is squeezing it. Several other missions from ESA and JAXA are in planning or approval stages, also timed to the encounter. The coverage will be the most concentrated in history for any single small body, which raises the obvious question, with all that hardware pointed at one tumbling rubble pile during one 6-hour window. What are we actually hoping to learn? What we're hoping to learn is whether everything we think we know about stopping one of these things is built on a false assumption. Here's the problem. Every deflection strategy we've developed, DART, kinetic impactors, gravity tractors, nuclear standoff bursts, was designed with a picture in mind. A solid rock, a coherent mass, something that transmits force the way a billiard ball does. You hit it, it moves. The physics is clean. Apophis is not that. And the uncomfortable truth is that most hazardous near-Earth asteroids probably aren't either. The rubble pile architecture, loose aggregate, minimal internal strength, held together more by gravity than by any actual binding, may be the default, not the exception. Hit a rubble pile the way we hit a solid rock, and you might just scatter it into a shotgun blast instead of nudging it aside. One threat becomes dozens. The deflection works perfectly and makes everything worse. No one knows the threshold. How loosely bound is too loosely bound? How much force crosses the line from nudge to fragmentation? Those answers require exactly the kind of interior data, density gradients, structural cohesion, how stress propagates through the body, that only a close flyby with the right instruments can provide. Which is why the strangeness of Apophis isn't just a scientific curiosity. It has stakes. So is 2029 really about Apophis, or about the next one? The next one. That's the real answer. Apophis is the rehearsal, 40,000 years in the making, for every loosely bound, tumbling, structurally ambiguous rock that will follow it across the centuries. Because here's what the orbital math tells us about the window we're standing in. An object this large, passing this close, happens roughly once every 40,000 years. Not once a generation, not once a century. Once in a span so long that the last time it occurred, modern humans were still painting cave walls in southern France. And it's happening in our lifetime. In April of 2029, a Friday the 13th, the kind of coincidence that would feel like fiction if the orbital mechanics didn't confirm it. A 340-meter world will pass within 32,000 kilometers of Earth's surface, and we will be watching with every instrument we've managed to build in those 40,000 years of waiting. The Yarkovsky drift that bent its trajectory, the rubble pile interior that shouldn't hold together, the tumbling that defies a simple spin. All of it resolved, or at least illuminated, in a single 6-hour window. So the question worth sitting with now isn't whether we're ready. It's what that night will actually feel like. Standing on a planet that's about to reach out and touch something ancient and strange and close enough to see. That night will be quiet, the way all historic nights are quiet. No sirens, no broadcasts, no one telling you what to feel. Just a moving point of light, slower than a satellite, brighter than most stars, crossing the sky in about an hour, visible to the naked eye for the first time in human history for an object this large. And we will know, by then, everything we need to know about why it passes without hitting us. The orbit calculated to a resolution of meters, a century of future encounters already checked and cleared. Earth's gravitational influence mapped down to the tidal stress on individual boulders. The mechanics are not mysterious. Apophis follows a path bent by every planet it has passed, nudged fractionally by the pressure of sunlight across decades, and that path brings it through a corridor 40,000 kilometers wide, which sounds terrifyingly narrow until you understand that we can predict that corridor to within hundreds of meters, and it does not contain us. The answer to how something this big passes this close without touching us is not luck. It is geometry, and we learned to read it. What we did not expect is what we learned about the rock itself, that it would be underdense, more rubble pile than stone, held together by its own weak gravity and almost nothing else. That it would be shaped like two lobes joined at a fragile neck, like something that nearly split apart and forgot to finish. That it would tumble in a way that violates the easy physics, wobbling on two axes at once, suggesting an interior that never settled, that carries the memory of some old collision it never quite recovered from. The strangeness was not in the danger. The strangeness was in the object. And the close past did not resolve that strangeness. It revealed it. On the night it comes, 1 billion people will tip their faces toward the sky. Apophis will cross the visible disk of the sky in roughly an hour, moving fast enough to watch with the naked eye, a star that doesn't belong to any constellation, drifting steadily south to north. Every telescope pointed at it will be measuring tidal stress in real time. Whether that fragile neck between the two lobes flexes, whether the tumble rate shifts, whether loose surface material migrates toward the equator or sheds entirely. This is the first time Earth's gravity has grabbed this body in millions of years, and a 340-meter object held together more by low gravity than by rock is exactly the kind of structure that stress tests at the worst possible moment. If the neck creaks even slightly, if the rotation period changes by a few minutes, the models that projected its path for the next century will need to be rebuilt from scratch. Scientists won't know the final answer on the night it passes. They'll spend years mining that data, running it backward and forward through every gravitational model we have, trying to close the gap between what we predicted and what we actually saw. A rock that is also a question, a sky event that is also an experiment. History going both ways at once.